Hi. So last class, we did two problems on relating delta U to delta H. And the last of those problems had to do with vaporizing. Let's see. $100 grams of water. So in other words, going from the liquid to the vapor. And so this was problem 2 of relating delta U to delta H. And what we found at the end of that problem was that delta U and delta H both were pretty large positive values. So I kind of wanted to talk a little bit about, why the delta U and the delta H, why they are positive for this process. Because I think we can learn about, delta H and delta U by looking at examples like this. So when you have water in the liquid state, it's, water molecules are attracted to each other by hydrogen bonds. And this is a stabilizing interaction. These are attractions. So molecules, they come together, they attract one another, and that's stabilizing. And so that's a lower energy situation than when molecules are separate and not attracting each other at all. So it's perfectly understandable why delta U and delta H would be positive for vaporizing water. So the reason is really that in the liquid, water molecules attract each other through hydrogen bonds. And that this stabilizes liquid water relative to the gas. Because there are no such stabilizing interactions in the gas phase. So this kind of goes along with, fix something here. This goes along with the need to add heat, right? To have this process happen, to add heat to turn liquid water into vapor, right? Because if the vapor is at a higher energy, then in order to get up to that energy, you have to get that energy from somewhere, and that energy comes from the heat that's going in. So, anyway, liquid water is more stable. Liquid water has a lower potential energy, and both the internal energy and the enthalpy of liquid water are lower than the corresponding quantity for the gas. So I guess I would say that U gas is greater than U liquid. So the delta U for liquid to gas is positive. And similarly, the H, the same thing exactly. The enthalpy of the gas is greater than the enthalpy of the liquid. Delta H for liquid to gas is positive. So, if you think, oh, I kind of understand internal energy, but I don't really understand enthalpy. It's, a strange word. What does it really mean? Really, it's really got the same stuff in it as internal energy. The only difference is that there's this little bit of work, or sometimes substantial amount of work that separates the two. But the reason for U gas being greater than U liquid is the same as the reason why H gas is greater than H liquid. This is because water is stabilized by hydrogen bonds. Okay, so it's the same. So it's not, the enthalpy is not really such a mystery, really. Okay. But like I said, you have to remember that they are not the same. And that's because of the work. When in a situation when work is done, they can be the same, but they're not the same when work is done. And that's because, delta U is Q plus W. If we have a constant pressure process, then this is QP, which is also delta H. So it's the work that distinguishes between them. Work is basically minus P delta V. It's a special case, but what you could see is that if the delta V is positive, that's an expansion, then the work is negative. And in this case, you could see if this is negative here, right, then you're adding something negative to the delta H, that in this case, you would have the delta H would be greater than the delta U because you're adding something negative. So U will be smaller than delta H. Okay. If there's no work done, then they're the same. So anyway, that's just a little bit on, the why you get positive delta U and delta H in that problem. So basically in this situation, the heating, the increase in internal energy is much more important than the work. So the main event really is the breaking of those hydrogen bonds. And yes, the system expands because you've created a gas, but it's a smaller fraction of the total. It's not as important magnitude wise. Most of the change in magnitude is due to the heat that goes in. Okay, so there's one other version, there's one other equation, one last equation that relates delta U and delta H, and that's this one. So if you remember, we had delta H is delta U plus delta PV, right? That H is U plus PV. That leads to this equation. And if we're talking about gases, then we can replace nRT with P. And if N and R are constant, then this becomes NR delta T. And that's the situation, that's the equation you use if N is constant, but the substance is heated or cooled and the temperature changes. So, but you don't have anything else going on really, like you don't have reactions or phase changes or things like that. Well, in a phase change, you would never have a delta T. So anyway, this is generally used in cases where, you just heat or cool a substance. And if it's a gas, then this delta T leads to a significant amount of work done, and then you can have a significant difference between delta U and delta H. So generally, we use this for heating or cooling gases. So I'd like to do an example of that, but I first need to talk about something called CP. So CP, which is called the heat capacity at constant pressure. We've been focusing on constant pressure because it's so important to us chemists. Anyway, CP shows up in a lot of problems where a substance is heated at constant pressure and, like I said, results in a temperature change. Okay, so before I do a problem, I want to talk about the heat capacity at constant pressure. So it's like just as the heat capacity at constant volume, right? This describes how the internal energy changes with temperature. So just as CV describes that. CP describes how H changes with temperature. Okay, so I'll do a similar thing. So if we write H as a function of P and T, so dH would then be dH dt at constant P dt plus partial H partial T at constant P dP. Okay, but if pressure is constant, then this dP is equal to 0. So this term goes away completely, and we end up with dH is dH dt at constant P dt. So I don't really know exactly how H changes with P. I can close my eyes, and I could draw a line or some kind of curve that just goes up, because I know that H is going to this should be T. It's going to increase with T. So the slope is equal to CP, right? dH dt, that's the slope of an H versus T graph, because it shows how H changes with T. Okay, so this dH dt at constant P is what we define as the heat capacity at constant pressure. Okay, and it shows, like I said, how enthalpy changes with temperature at constant pressure. So if I go at constant pressure, right, then P isn't changing, so I don't even have to think about this as a partial derivative anymore. I could just write it as a regular derivative. Okay, so I have this formula, and then that means dH is CP dt. Okay, and I can integrate this. So I get delta H is, now here, I have to stick in a number of moles. And how am I justified in doing this? It's because CP is always a per mole quantity. So I have to put that N in there. And now if I can take CP out of the integral sign, so the condition really is if CP is constant over the temperature range, okay, then I can take it out. CP is really not constant over a very, very wide temperature range, but it's okay for small delta T's. So it's really an approximation to assume this. But if you do assume that, then the delta H would be NCP times T2 minus T1, or NCP delta T. This is if CP is constant over the range delta T. But if CP is not constant, then I cannot get any simpler than this equation. And I would have to know, how does CP change with T, right? This is really going to be CP of T, function of T. And actually, heat capacities are well known at different temperatures for commonly used substances. And I'm going to show you I have a special problem where you'll actually use the dependence of CP on temperature. But that's not what I want to do next. I'm going to do something else first, because here we are talking about CP. And so I'd like to talk about the relationship between CP and CV. Okay, so we know that delta U and delta H are related by these very specific equations that we use for different types of problems in different conditions. So so delta U and delta H are related in a known way. What about CP and CV? Are they related? Are they the same? So that's kind of what I'd like to address next. Okay, so we know that delta U is the heat that flows at constant volume, which is NCV delta T. I'm assuming CV is constant. So these are known. We also know that delta H, the heat that flows at constant pressure, is NCP delta T. Okay, so let's suppose that we heat a sample, 1 mole sample of gas at constant pressure versus a constant volume. So let's draw a constant volume container here. Okay. Okay, there's some molecules in it, and it has fixed walls. And it starts at T1. And we're going to add heat until the temperature becomes T2. That heat is going to flow at constant volume, right? Because the volume is constant. So add heat until T1 goes to T2. Okay, and I'm going to contrast with this with the situation where I don't have a constant volume container, I have a constant pressure container. Okay, so this is a movable wall. And it has, let's say, atmospheric pressure pushing on it like a piston. Okay, so now I'm gonna do the same thing. Starts at T1. I'm gonna add heat until the temperature becomes T2. So I'm gonna add heat QP. Okay, and I'm gonna add heat, like I said, until the temperature, we want the same temperature change here. So the question is, which of these processes would require more heat, or is it the same amount of heat? Okay. So let's think about what happens when we add this heat. So when we add heat at constant pressure, and in addition to increasing the temperature, this piston is going to move up, right? The wall moves up. The gas expands. Well, in terms of energy, that's doing work, all right? So the gas does work, okay? So to get the same temperature rise on the right, at constant pressure, this is the constant pressure side, constant volume side, okay? So to get the same temperature rise at constant pressure, let's think about it. You know, we have, we'll have to add more heat because some of the energy from that heat is going into doing work. Okay, so because some of the energy from heat on the right goes to doing work, you need to add more heat to get the same temperature rise. And of course, I'm talking about at constant pressure. So that means that QP is greater than QV in this situation. Okay. Well, QP is NCP delta T. QV is NCV delta T. Let's look at what's the same here. N is, of course, the same. Talking about, did I ever say 1 mole? But I meant 1 mole, same amount of gas in each. Let's call it 1 mole. Okay. The delta T, well, the way to define the problem, the temperature rise is the same. So if QP is greater than QV, it implies that CP must be greater than CV. And that is indeed the case, that the heat capacity at constant pressure is greater than the heat capacity at constant volume. Now, if you recall that equation I was talking about, remember we had this, right? And this became delta nRT. So this is NCV delta T for delta U. And this is plus delta, this becomes NR delta T because N is constant. I'll talk about heating, no change in moles. Oh, and N delta H, of course, is NCP delta T. So if you look at this and you cancel the N's and you cancel the delta T's, you get CP equals CV plus R. Now, let me tell you, this is really not a real proof. It's just for this special case. But it turns out that this is generally true, but it is. I didn't prove it, but it is true that for gases, CP equals CV plus R. And all you have to do, if you know the CV, to get the CP is add R. And all you have to do to get, if you're given CP and you need to get CV, is subtract R. You know, these have the same units, right? Joules per mole Kelvin. That's the units of R, it's the units of CP. So this is generally true for gases. If you wanted to actually prove this, I have to write like 3 or 4 pages of differentials and all kinds of math, and we're not doing that this year. Okay, what you will often see, so often CV and or CP is given as a multiple sort of of the gas constant R. And let me just show you the very simplest example is for a monatomic ideal gas. So U is 3/2 RT. What would du dt be? Right, remember CV would be that. It would simply be 3/2 R. And CP would be 3/2 R plus R, which is 5/2 R. So a lot of times you're given values of CV and CP that are like this. And in the problem I'm going to talk about, well, actually, in this problem, you're not given values like that, but in another problem later, it's good to know that you can, well, let's just forget until I get to that, and then I'll tell you what I'm talking about. All right, so so this CP equals CV plus R is really for gases only. It is not the case for solids and liquids. So let me talk just a little bit about that. So when we went back, when we looked at this situation here, we compared what happens at constant volume to what happens at constant pressure. And the reason why there was a difference between CP and CV is because at constant pressure, the gas expands and does work. And it's that work that creates the difference between delta H and delta U. And it's also the reason for the difference between CP and CV. But for solids and liquids, on heating, there's not much expansion compared to a gas. And so as a result, CP and CV are almost the same for solids and liquids. And that's due to the lack of expansion. I mean, there is liquids do expand when you heat them, but they don't expand like a gas does. And so CP and CV are much closer to each other in the liquid or solid. Okay. So I have another special problem. It's called a special problem on heating nitrogen. All right, here it is. So I think what I'll do is start you on this problem. You know, if you want, you can turn the video off and try to think about some of these things yourself and then come back. Nitrogen has CV of 20.815 joules per mole Kelvin. So what would CP be? So this is a very simple CP equals CV plus R. So it's 20.815 plus 8.314 or 29.129 joules per mole Kelvin. So that's all that is all about. Now it says, suppose the heat capacity of nitrogen is constant in the 100 to 300 temperature range. So that would mean, well, so then it says if 2 moles are heated from 100 to 300, what is delta H? So now we use that delta H is NCP delta T, which is an approximation, because if you remember when we integrated DH is NCP dt, we had to assume that CP was constant in this temperature range. But here we're told that you can't assume that, okay? So that would mean that the delta H is simply 2 moles times the CP that we just calculated times 3, oh yeah, so the delta T, which is 300 minus 100 degree, actually Kelvin doesn't matter, but this is Kelvin, so I'll write it as Kelvin. So that's just 200. And when you do the math, it comes out to 11652 kilojoules, but it's only 3 sig figs. These numbers are only given to 3 sig figs, so it's 11.7 kilojoules. So that's the delta H. Now it asks, what is the delta U for this process? So delta U, you know, you could do it a couple of different ways. You can use NCV delta T, which is just 2 times the CV, which is given, times 200, right? Because it's 300 minus 100. And that's 8.33 kilojoules. So it's like 8,330 joules, which I converted to kilojoules. You could also do this as delta U is delta H. Yeah, delta H. Right, so we actually have delta H is delta U plus NR delta T. I just want to flip back and make sure that I didn't make a mistake earlier on that. Let me see. I did that. Yeah, because this is delta H is delta U plus that. So so delta U would be, yeah, that's right. I have the plus in there as it should be. But if you're finding delta U, that's going to be delta H minus NR delta T. Okay, so that would be 11652 joules minus 2, 8.314, 200. Just want to check this. Just had to find my calculator. So it comes out to 8326 or 8.33 kilojoules, which is, of course, exactly the same as this. So you can do it either way. Okay. Now, this last part is the tough part. All right. So this shows you what to do if you're given, I don't know why I did that. If you're given the actual way in which CV depends on T. So here, this is often the way the heat capacity at constant pressure is fitted to a temperature curve. So CP kind of looks like this. So if you're in this range here, whatever that is for the particular gas, then CP is more or less constant. But if you're in this range over here, then it's not very constant. And this curve, this function sort of describes how CP does depend on T. And there's a very definite reason for why it depends on T, which we're not covering this semester. So we have CP equals, so this is the way it's a constant term, a linear term in T, and then this weird constant divided by T squared term. And the values of these things are given here. Okay. So now if you're going to figure out delta H as the number of moles times the integral of CP dt, now you've got to integrate this. So now you have A plus BT plus C over T squared dt. And when you have an integral that's a sum, you separate it into separate integrals. We just call this C over T squared. Okay. So you have 3 separate terms. So now you integrate term by term. Okay. So you know how to integrate A dt, take the A out, right? This is going to be A integral of dt. This is going to be B, the integral of T dt. This is going to C 1 over T squared dt. So you have to integrate these each term by term. And I recommend that you do this before you plunk in the values of A, B, and C, because you don't want to be carrying these crazy values of 10 to the minus third and 10 to the fifth as you do your calculation. You want to get the answer in terms of A, B, and C, and then lastly, you know, after doing the integrals, you want to plug in the values of A, B, and C. Okay, and when you do this problem, you will come up with an answer for the delta H, and you will see that that it doesn't matter that much that we assume that CP was constant. Okay, that the answers are really pretty close. but be careful because, there's some pitfalls in this problem. You have to watch your signs. And if you don't know what an integral is, find out. Okay. Okay. So what's next? So I told you a while ago that PChem tends to focus on, oh, by the way, this special problem is going to be due on Monday, November 1. I'm going to have 2 problems due that day, but I know we have an exam on Wednesday, October 27th. So we won't be having any special problems due then. All right, so moving right along. I told you at one point that in PChem, we tend to look at idealized processes. So while you have an expansion in real life, which that isn't, okay, so we might say an isothermal expansion. Now, in real life, you might never have a truly isothermal expansion where the temperature is constant. But in PChem, we want to handle the simple cases first. We want to know what happens in an isothermal expansion when all the heat needed for the work is flowing in and the delta U is 0, at least for gases, ideal gases. So one idealized process that we looked at so far is the isothermal expansion. And actually, we then branched into 2 separate. We branched into the reversible isothermal and the constant pressure isothermal, even though there could very well be expansions that are not quite reversible and, not quite constant pressure either. So now we're going to look at another such idealized expansion. And this is kind of on the other end of the spectrum. So in the isothermal expansion, the delta U is equal to 0. The temperature is constant. So the other idealized expansion is the adiabatic expansion. And in an adiabatic expansion, no heat exchanges between the system and the surroundings, which is to say Q is equal to 0. Okay, so what this means is if you have an expansion, but Q is 0, right? Remember, delta U is Q plus W. If Q is equal to 0, then delta U is the work. So that means that if the system expands and it does work, then the internal energy, then the delta U must be negative, which in turn implies that the internal energy drops. What does that mean? If we're talking about an ideal gas, what does that mean for the temperature? It means the temperature drops. Okay, so in an adiabatic expansion, so basically we put insulation around the system. So there's no heat flow. Any work that's done is at the expense of the system's internal energy. Okay, so we're going to have a drop in the temperature. And this is actually a very important thing to know, because in order to be able to calculate the change in internal, we want to be able to calculate the change in internal energy, the change in enthalpy, and the work. In order to be able to calculate that, we need to know what the final temperature is. Okay, so finding the final temperature for adiabatic expansions is our next topic. Okay, and then we'll use this delta T to be able to calculate delta H, delta U, W, Q, we know is already 0. Yeah, later we'll calculate entropy changes, but not now. Okay. So how do we get this final temperature? Well, first of all, it depends on the type of adiabatic expansion. So there are two main, like I said, idealized situations. So we have the first is the adiabatic reversible expansion, and the second is the adiabatic constant pressure expansion. Okay, so we're aiming to get this delta T, so we have to find T2. So we start with two things that we know. We start with the first law and this fact that du is ncv dt. So the first law in differential form is dq is du plus dw. And then we use the, oh, wait a minute, what did I write there? du, sorry, is dq plus dw, and dq is equal to 0. Why? Because it's adiabatic. So we have du equals dw, but du is ncv dt. So this is where we start. Okay. So, and you could see that we have these differentials in here. So eventually we are going to have to integrate. All right. So what do we do? Okay. So first thing we do is we use the definition of expansion work, which is minus P external dV. So we have minus P external dV. Okay, and now we're going to use the fact that this is a reversible expansion. So P external is the same. So the external pressure is the same as the pressure of the gas. So lots of times I write P external equals P gas, but we never say P gas. We just say P. So this NCV dt equals minus P dV. And then we need to put in, because we have a dV here, eventually going to integrate volume. We know that P depends on V, so we better put that in. And so we have this. And now when you integrate both sides of an equation, oh, what happened there? What is this? It's weird. So before I can integrate both sides of this equation, I need to move the temperature over to this side because I have a dt on this side. So I have to kind of group variables, ncv dt over t, right? I have to divide both sides by t. So this is what I have. And then I'm going to cancel the n's because they're annoying me. And then I check to see if I have the same thing that I have in my notes, which I do. And now I'm going to integrate. Okay, so this is over temperature. So this integral goes from T1 to T2. This one goes from V1 to V2. And so I can take the CV out. And then the integral of dt over t is natural log of t. I'm going to take the r out. And this is natural log of v evaluated over the limits. So this is CV log T2 minus CV, well, let's just put it in parentheses, log T1, which of course is CV log T2 over T1. I'm just going to skip that step here and call this the log V2 over V1. Okay, now here's the thing. So I should write some of these things down, what I've been telling you. So let's see, cancel the ends. Move T to left side. Cancel the ends because we're grouping like variables. Then I integrate. CV constant is assumed. Now here, I have a formula, but problems do not generally give the initial and final volume of the expansion. They give the pressures. So I need to substitute, I need to write this in terms of pressures. And you could see now because I have a process that's changing the pressure and changing the volume, and the temperature is not constant, that I have to use P1V1 over T1 is P2V2 over T2, right? Which means that if I want V2 over V1, so I just move the V1, I move that over to this side. And now if I move T2 to the left on top, and this will go here on the bottom. So it'll be P1 over P2, T2 over T1 equals V2 over V1. So a little algebra. If you didn't like mine, you can do it slower. But CV, you get the idea, log T2 over T1 equals minus R log P1 over P2, T2 over T1. And now again, I'm going to have to group put all my T's on one side, all my P's on one side. And now what I'm going to do is write this, because this is the rule of logs. This is minus R times the log of A, B is minus R times the log of A, I'll call this A, minus R times the log of B. Right, so I separate that out, and now I see that I can take and move this term to the other side. And when I do that, I get CV log T2 over T1 plus R log T2 over T1 equals minus R. What, did I forget the log here? I did. Okay. And look at this. This is what's nice, is now I can factor out this CV plus R. Right, and now I know that's CP, because we just worked with that. So I have CP log T2 over T1 is minus R log P1 over P2. And what I'm solving for is T2. I know what T1 is. I presumably know the two pressures, initial and the final, in this adiabatic expansion. So I'm just going to put the CP on the other side as I solve for T2. So the natural log of T2 minus the natural log of T1 is this. So now I'm going to move this to the other side. And I'll have natural log of T1 minus R log P1 over P2 divided by CP is the natural log of T2. So if I calculate this, that is the natural log of T2. And so I'm going to have to take the, e to that number to get what the T2 is. Okay. So, yeah. So what I want to show you now, so the way to get T2 is you calculate this and take the inverse ln to get T2 or e to the whatever, okay? Once you get T2, so now if you have T2, how do you get the rest? Delta U, even delta H, Q, W, right? So it's so easy. Delta U is NCV delta T. Once you know delta T, that's just T2 minus T1. So you presumably given T1, and you just calculated T2 from T1. Delta H is NCP delta T. W is delta U, and Q equals 0. Okay? So note, by the way, that Q is not equal to delta H here. That's because the pressure of this gas is not constant. You need to have a constant pressure situation for the system in order for Q to equal delta H. All right. So I do have a special problem on adiabatic expansions, which I'm going to show you in a minute. But what I first want to do is show you sort of how the pressure changes as the volume increases in an adiabatic expansion. So I want to sort of show you by starting with what it did for the reversible expansion. So in the isothermal expansion, so this is an isotherm here. So as that gas expanded, its pressure drops along the isotherm, and the work is the area underneath, right? So this is the work for reversible isothermal expansion. Okay, we talked about this another time. So how does it differ for the adiabatic case? Okay, and actually there's a pretty big difference, because during an adiabatic expansion, the temperature is dropping. So here, the temperature is dropping. So you start at one isotherm at a higher temperature, and you end up at another isotherm at a lower temperature. So this is T2, which is lower, and this is T1. So you may start here, but you don't end up on the same isotherm like you do here. You end up down here. So what happens is that the temperature decreases more steeply. I'm not doing a very good job drawing it here, but there we go. So you might start here, but you're going to have a steeper drop in pressure as the volume increases. And that's because as you're going along, the temperature is going down also. And of course, you know that pressure varies with temperature in a proportional way, at least if volume were constant. So now you have to take both of those things into account. So, you know, you could see that according to the slope issue, you know, you have a steeper slope here. So, you know, you're going to have less work done, but it's not even fair to compare because the final volumes are different for the isothermal and adiabatic cases. The reversible expansion, the final volume ends up being a lot larger because you're at a higher temperature. Adiabatic, because the temperature has dropped, you end up at a lower volume. So you don't end up at the same volume. So you really can't compare these two that easily, like you could for, say, isothermal reversible and isothermal constant pressure. There you end up at the same final state, starting at the same initial state. When you compare to adiabatic, you start at the same state, but you don't end up at the same state for reversible adiabatic and reversible isothermal. So the problem that I give out this, oh, wait, there's one more thing I have to say before then. And that is what happens in an adiabatic constant pressure expansion. Okay, and I'm not going to go over that derivation, but it's on a video by that name. I think it says, well, let me see if I can find it. I think it's called Finding Final Temperature for Adiabatic Constant Pressure Expansion. Yeah, it's called Final Temperature for Constant Pressure Adiabatic Expansion. So that video shows how to get T2 for adiabatic constant pressure case. Okay. So you should watch that one first. And then you should do this special problem. So I'm going to show you the special problem. So here is the whole thing. Okay, so I'm asking you to compare and contrast the adiabatic reversible expansion to the adiabatic constant pressure expansion of the same gas. So you have to calculate delta T, which means you have to get T2 for both. Then you do those very simple calculations. Well, Q is 0. You know, delta U is going to be NCV delta T. Delta H is NCP delta T. W is simply delta U. So once you get T2, those calculations are easy. So here's the two equations, the results really. This one is the one we just derived. And this one is on the video. Okay. And then you'll fill in this table, you know, this is given. You'll put in your T2s, you find your delta T, delta U, W, Q. But what I also would like you to do is to draw graphs that compare these situations. So what I do is I give you these graphs of these three isotherms. So this is the isotherm for the starting temperature. This is the isotherm for T2 for the constant pressure expansion. And this is the isotherm for T2 for the reversible expansion, right? And so you end up at different volumes because if this is your pressure at the end, say 0.1 atmospheres, your final volume for the reversible, you'll start here and you'll end up down here. you'll have the greatest decrease in temperature because you're doing the most work. And you know what? I talk about this. I want you to take a look at this, but there's a video already posted from October 21, 2020, where I talk about this. Okay, so I'd like you to, you could watch that, and that'll help you with this part, with explaining what to do and such. And it even kind of does part of it for you. So just watch that video. That's the next video in the sequence. I think I'm more or less done with making new videos. I think I have all the videos from here on to the end of the semester. So I'll be just telling you which one corresponds. So this talks about this and goes on to thermochemistry. And I will start thermochemistry on Monday, the 25th. I don't know how far I'll get, but this video starts with going over this adiabatic special problem. This is also due Monday, November 1. And so it starts by talking about this special problem, and it goes on to thermochemistry. And I will go as far as thermochemistry as I can on Monday, October 25th. And then you'll be able to watch this video. It goes up to standard enthalpies of formation. And then, I will, of course, continue in class and tell you what videos you need to watch. But anyway, that's it for now. And I will see you in class. Good luck studying.